Continuing this series of videos on receiver design, today we're going to talk about mixers. And we'll talk about some basic mixer theory and operation, and we'll look at some different types of mixers, but we're going to primarily focus on quadrature mixers. And we'll talk a bit about how they work and why you might want to use one, and of course, we'll look at some practical circuit implementations as well. Now, before we talk about quadrature mixers, it's probably a good idea to do a quick review on what a mixer is and how it works. Now in RF, when we talk about a mixer, we're usually talking about a multiplying mixer. So that's going to take two inputs at some frequency. So we'll have an RF frequency and a local oscillator frequency. And it's going to multiply those two sine waves at those two different frequencies. And it's going to output the result of that multiplication. And from trigonometry, we know that if you multiply two sine waves, you're going to get the sum and difference frequencies on the output. So an ideal multiplying mixer would take in two sine waves at two different frequencies, and it would output the sum and difference frequencies. However, since most mixers are implemented using diodes or transistors, you might be left wondering who taught diodes how to do trig. Well, of course, diodes don't know anything about trig identities, but they do make very good switches. And fundamentally, that's exactly what a mixer is. It's a switch where you have some RF signal applied to the switch input, and that switch is turned on and off by your local oscillator signal. So what you have on the intermediate frequency, or IF port of the mixer, is that RF signal chopped up at the rate of your local oscillator frequency. So, for example, if I have a 5 Hz signal applied to my RF port of the mixer, and a 3 Hz signal applied to the local oscillator port of the mixer, then we'll see that over a 1 second period, that 5 Hz signal will get chopped up 3 times. And you can see this is effectively multiplying by 1 and 0. So when the switch is on, it's basically multiplying that RF signal by 1, and when the switch is off, it's effectively multiplying the RF signal by 0. And it's this multiplication using a switch at the rate of the local oscillator's signal that provides us that sinusoidal multiplication that we need. And we know, based on the trig identities, that if we're multiplying two sinusoidal signals together, then we're going to get the sum and difference frequencies of those two signals on the output. So if you actually were to look at the frequency content of this waveform, you would see that it would in fact contain the sum and difference frequencies of the RF and LO inputs. So not all mixers work exactly in this manner. There are different types of mixers. For example, some mixers multiply by 1 and -1 instead of 1 and 0. However, the fundamental idea of using a diode or a transistor as a switch in order to do this multiplication is the same. Now, of course, in the real world, things tend to get a bit messier. So let's take a look at the output of a real mixer. In this case, it's a Mini Circuits TUF1 double balance mixer. When we apply a 5 MHz signal to its RF port and a 3 MHz signal to its local oscillator port. Now we can clearly see in the time domain that our 5 MHz RF input signal has in fact been chopped up on the output. However, it's very difficult in the time domain to identify what the actual frequency content of this output signal is. And that's why it can be very useful to look at these signals in the frequency domain. Now, in an ideal mixer, we would expect to only see the sum and difference of our two input signals, which are at 3 and 5 MHz. And we do in fact have the sum and difference frequencies. We have 8 MHz signal here, which is the sum, and we have a 2 MHz signal here, which is the difference frequency. And you can see that those are the two most prominent frequencies in our output. However, there's a lot more going on here. Part of that is due to the fact that we have some leakage here. We have our 3 MHz and 5 MHz signals leaking through. But a lot of it is due to the harmonic content of our input signals getting mixed together, as well as reflections coming back into the mixer from the IF port, and those get remixed with our input signals and their harmonics and all kinds of things. So you get lots of additional harmonic content on the output that you really don't want. And so it's just important to realize that when you're using a real-world mixer, you don't just get the sum and difference frequencies. You get a lot more junk. And usually it's very easy to filter that out. For example, if we were only interested in the difference frequency here at 2 megahertz, we'd just stick a low-pass filter on the output of the mixer, and that would knock out all of this higher frequency content. And what this is used for is frequency conversion. So let's say that you're transmitting a signal at 10 megahertz. And let's say it's just a steady carrier wave. You're not modulating it at all. It's just a steady tone, if you will, at 10 megahertz. Now, if I tune my receiver to 10.001 megahertz, that means that I am 1 kilohertz away from your 10 megahertz signal. And if I feed your 10 megahertz RF signal and my local oscillator signal at 10.001 megahertz into a mixer, the output's going to be the sum, which would be 20.001 megahertz, and the difference frequencies, which the difference obviously is at 1 kilohertz. And so this is a very common use of a mixer in a receiver, is for down conversion. I've basically taken your higher frequency signal at 10 megahertz and down converted it to 1 kilohertz. And when you're down converting, you usually take the sum component and throw it away, typically just with a simple low pass filter. So what's interesting is that this 1 kilohertz signal that I've down converted has the same properties as the signal that you transmitted at 10 megahertz, only it's now at 1 kilohertz, which is actually in the audible range of frequencies. So once I do this down conversion from 10 megahertz to 1 kilohertz, I can take this output and simply feed it into a speaker and hear your signal that you're transmitting at 10 megahertz. So I have this little function generator here outputting two signals. Right now they're both at 10 megahertz. And I'm just feeding those into that TUF1 mixer. And I'm taking the IF out from that, and I'm just putting it into this little Radio Shack speaker here so we can hear the difference as we tune our local oscillator signal. So if I move this frequency up by 1 kilohertz, we hear a 1 kilohertz tone. If I move it up by 2 kilohertz, we hear a 2 kilohertz tone. So I can tune, and as I tune, I can hear the 10 megahertz signal on the RF port being down converted to different frequencies. And likewise, if I'm transmitting a signal and you're listening on 10 megahertz, I can change my transmit frequency slightly so that you hear different tones at different times. So that's really just basically frequency modulation. And it works well, and it's very simple, but it does have some problems. And the biggest problem is that of image frequencies. So we know that if we tune our local oscillator to 10.001 megahertz, that's 1 kilohertz away from our desired 10 megahertz signal. And when they're mixed in the mixer, it will produce the sum and difference of those two frequencies, and one of those resulting frequencies will be our 1 kilohertz tone that we just heard. However, because the mixer will produce both the sum and the difference of any frequencies that it sees, if there is another transmitter transmitting 1 kilohertz above our local oscillator at 10.002 megahertz, well, that also will generate a 1 kilohertz tone. And this is a particularly bad problem for these direct conversion designs, where we're converting an RF signal directly down to a low frequency baseband signal, because the unwanted image frequency is so close to the desired frequency that we can't filter it out at all in the RF front end, because they're just too close. We can't build a tight enough filter to take that image frequency out. So unfortunately, there's really no way that we can distinguish, in this case, between this unwanted image signal and our desired 10 megahertz RF signal. So if I tune up by 1 kilohertz, I hear a 1 kilohertz tone. But if I tune down by 1 kilohertz, I also hear a 1 kilohertz tone. So there's really no way to easily distinguish between a frequency that is 1 kilohertz above or 1 kilohertz below my local oscillator. And the reason that we can't tell the difference between a frequency that's above or below our local oscillator is that in this configuration with a single mixer, we're not getting really all the information about the signal that we need in order to make that determination. So clearly we have the amplitude of the signal, and we have the frequency of the signal, right? We can count the period and calculate the frequency here. But there's a third component to a signal, which is the phase. And we really can't tell the phase of this signal because we have no reference for the phase. And to demonstrate that, I'm currently changing the phase of this signal. I'm rotating it through a full 360-degree phase shift. And there's obviously no change in the output here. Now, yeah, maybe if there's a sudden instantaneous change, like a sudden inversion here, you'd see a little blip very briefly. But unless you happen to catch that really brief blip, you're not going to tell if that phase had changed or not. However, if I provide a reference waveform, I can change the phase of that signal, and that we can see very clearly that now that we have a reference waveform to compare against, that phase is clearly changing over time here. So what we need is some sort of reference so that we can determine the phase of a signal, because that's the third component of a signal that we're currently missing. So to demonstrate that, consider these two signals here. They're both currently in the same phase at the same frequency. However, if I take channel 2 here and I increase its frequency to be above channel 1's frequency, you can see that it looks like it has this continuous phase slip in the left direction. Likewise, if I make channel 2 slightly below channel 1's frequency, now we have this continual phase shift in the right direction. So if I have this phase information, I can tell which direction the signal is with reference to my local oscillator. So how do we recover this phase information that we're missing? Well, to understand that, it's important to understand that we can represent signals in different ways. And it's the same data, it's the same signal, we're just looking at it from a different perspective. So for example, we can take the number 2 and just call it 2, or we can represent it as the sum of two smaller numbers, such as 1 plus 1. Likewise, we can take a larger signal and represent it as the sum of two smaller signals, just like the oscilloscope's doing here with this math waveform. It's taking these two signals, which are 90 degrees out of phase with each other, and it's simply summing them together, and we get this larger waveform. So what's interesting here is that if we take, say, the amplitude of one of these signals and we start increasing it, of course it's going to increase the amplitude of the sum waveform, but it also is changing the phase. We can see that the phase is shifting here as we increase and decrease the amplitude of channel 2. So if we can somehow take our signal and deconstruct it into these two smaller components, two smaller waveforms that are 90 degrees out of phase with each other, we can calculate all the information we need about this larger signal, right? We can calculate the frequency because these two signals have the same frequency as the resulting sum. We can calculate the amplitude, obviously, just by adding the amplitudes of these two together as we go along at different points in time. But we can also calculate the phase. And again, the oscilloscope is currently doing exactly that when it's generating this math waveform, which is the sum of these two smaller signals. Now, W2AEW has done some really good videos on quadrature signals, and that's what these are because they're simply 90 degrees out of phase. They're called quadrature, and that's all quadrature is. So I'd highly recommend that you go watch those videos if you want some more information about quadrature signals and how they're used to modulate and create these larger waveforms. However, for our purposes, we want to figure out how to deconstruct this larger signal into these two smaller components. So for right now, it's just important to realize that you can represent a larger signal by two smaller signals that are 90 degrees out of phase. Now, the mathematician Euler showed that when you have two signals that are out of phase by 90 degrees, represented here by this cosine and sine, you can represent them by e to the j omega t, where e is Euler's number, j is the square root of -1, so we're dealing with a complex value here. Omega is just 2 pi times the frequency of the signal, and t is time. And you can see that these two signals have the same frequency because they both have the same omega t in them. They're just shifted by 90 degrees because one is a cosine and the other is a sine. So when we have a signal that is positive with respect to our local oscillator, that's represented by this e to the j omega t. And we can see that the output of this, right, the sum of these two sine and cosine, if we were to break it down into those two components, we'd see that the cosine value here is leading the sine value by 90 degrees, right? However, if we have a signal that is negative with respect to our local oscillator, in other words, it's at a lower frequency, below our local oscillator, that's represented by e to the negative j omega t, because it is a negative frequency with respect to our local oscillator. And you can see the difference between these two, the only difference, is that we've inverted the sine component. Right? It's gone from cosine plus sine to cosine minus sine. And whenever you invert a signal, that's simply represented as a phase shift of 180 degrees when you're looking at it on an oscilloscope. So what you'll see is that for frequencies that are below our local oscillator, now suddenly the sine component is leading the cosine component here. So we can look at this phase relationship between these two signals, right? If we break our larger signal down into these two components, cosine and sine, we can look at their phase relationship and determine if a signal is above or below our local oscillator's frequency. And this is all that's meant by I and Q when you're talking about in phase and quadrature phase, right? The in phase component is a value that is static. It's kind of our reference signal here, right? Because its sign doesn't change when we have a positive or a negative frequency. And we have our quadrature component, and we can see the sign here is multiplied by j, which is the square root of -1. So this is sometimes called the imaginary signal, but I think that's a bit of a confusing term, so we'll just stick with the term quadrature here. And since that signal's phase changes depending on whether the frequency is above or below our local oscillator, we can simply compare its phase to our reference cosine phase and determine if it's above or below our local oscillator frequency. And so we've now recovered this phase information that we need in order to make that determination of whether a signal is above or below our local oscillator. So now we just have to figure out how we can force our mixer to provide us these two signals instead of the one signal that it's currently providing. And the way we do that is very simple. We just use two mixers. So we take the RF input signal and we feed that same RF signal into both of those mixers. However, the local oscillator signal that we provide to those two mixers is shifted by 90 degrees. So we have one cosine signal going into this top mixer, and we phase shift that signal by 90 degrees. So we provide a sine signal into this second mixer. So when we take the RF signal and mix it with our cosine component, we get our in-phase output, our I. And when we take that same RF signal and mix it with a sine component, our 90-degree phase shifted component, we get our Q output, our quadrature signal. So we can build this circuit. It's very simple. We really just need two mixers here and a quadrature oscillator. In other words, an oscillator that provides two signals that are 90 degrees out of phase. And we've actually talked about that in a previous video, so I won't cover that here, but it's very simple. You can just do that with a dual D-type flip-flop. And once we build this circuit, we can actually then take the I and Q outputs and look at them on the oscilloscope. And then we can see, as we change our RF signal from being above and below our local oscillator frequency, if we actually see that phase shift in the quadrature output that Euler's equations predict. And I've put together just such a circuit here. I have a quadrature mixer that's being fed with a 3 megahertz local oscillator, and again I'm outputting both a sine and cosine component from that local oscillator into the quadrature mixer. And I also have a 3 megahertz RF signal being fed into the Quadrature Mixer. And we can take a look at the I and Q outputs from that Quadrature Mixer on the oscilloscope. And I've connected channel 1 to the I output of the mixer and channel 2 to the Q output. Now we can see that my RF signal is 6 Hertz away from my local oscillator. And we can tell that it is above the local oscillator by 6 Hertz because we can see that my I output is currently leading my Q output. However, as I bring the RF signal down in frequency, we of course can see that the frequency output from the mixer is decreasing, and we still have this same phase relationship between I and Q. And if I tune down a little farther, we can see that here I'm basically right at the same frequency as my local oscillator. So this is, practically DC output here. But as I come up on the other side here, I'm now 4 Hertz away from my local oscillator, but we can see there's been a change in this phase relationship between I and Q. The Q signal is now leading the I signal. So we can tell that I'm now 4 Hertz below the local oscillator, whereas before I was 6 Hertz above. And we can see that transition very clearly here. I was slightly below the local oscillator frequency because we can see that the Q component is leading the I component. However, I made a sudden change in the output of my RF signal so that it was suddenly above my local oscillator frequency, and we can see that that Q component suddenly did a phase shift here. And so now the I component is leading the Q component. And that's exactly what Euler's equations predict. So this I and Q stuff isn't just, weird, abstract, imaginary math stuff. It's a real thing. We can actually take these I and Q components and construct signals with them, and we can take those signals and deconstruct them down into the I and Q, and we can see that I and Q behave exactly as Euler's equations predict. Now, for the practical implementation of a quadrature mixer, we could use 2 of these passive double balanced mixers, such as this Tough 1 from Mini Circuits. And these are very popular mixers, they work very well, but they do have some drawbacks. First of all, for a quadrature mixer, we'd need 2 of them, which means we'd have to split the input's RF signal between the 2, and we'd automatically lose 3 dB of power by splitting it that way. They also have an insertion loss of 7 dB because they're passive devices, so we lose a total of at least 10 dB there. Now they do have very high third order intercept figures, meaning that they're relatively immune to being overloaded by strong signals, but they get that high IP3 by having a strong local oscillator driving them. So you need typically about 7 dB output from your oscillator in order to optimally drive this mixer. And on top of that, they're relatively expensive. Even in large quantities, they're about $8 a piece. So for most implementations of quadrature mixers, at least in homebrew equipment, you'll find them use these little 4-to-1 multiplexer ICs instead. And these are commonly referred to as Tayloe mixers after Dan Tayloe, who popularized the idea. And it's really very clever because you only need 1 of these chips. They're very cheap, about 50 cents a piece. They require very low local oscillator drive levels, so you don't need a lot of power out of your local oscillator. And they still have a nice high third order intercept, so they're still fairly immune to being overloaded by strong signals. And on top of all that, they have very low insertion loss, less than 1 dB. So let's take a look at how you can use one of these 4-to-1 multiplexer chips as a mixer. Now the way that a 4-to-1 multiplexer switch works is you have 1 input and 4 outputs, and you can select which output is connected to the input based on the binary code that you provided. And it's just a 2-bit code, so you have S0 and S1. And for example, if you set both of those to 0, then your output will be on this channel. If you set S0 high but S1 low, then your output will be on this channel. If you set S0 low and S1 high, then your output would be on this channel. And if you set both of them high, your output would be on this 4th channel. Now remember that a mixer is really just a switch. So we can use this as basically a four-way mixer. If we apply our RF to the input here and take our output from these four channels. And the way that we switch between these four channels is we apply that quadrature signal from our local oscillator into the binary input code here. Now we can see from our quadrature input here that we're going to cycle through all of these states when we apply that quadrature input to these binary codes. So we have a state where they're both high, we have a state where they're both low, and we have the other two states where one's high and the other's low, and vice versa. So we can switch between all four of these in sequence by applying our quadrature local oscillator to the binary input code here for the multiplexer switch. Now, let's take a look at how that gets us our I and Q output. The mixing action of the 4-to-1 multiplexer is probably best understood if we assume that we're inputting two signals, one to the RF input here and one from our local oscillator, that are at the exact same frequency and in the same phase. So if we do that, we know that our quadrature input from the local oscillator is going to switch between all four outputs in sequence. So the first output in red here is going to see the first quarter cycle of the RF input, and in fact it's going to start sampling at 0 degrees. We're then going to switch to the second output in blue, and it's going to start sampling at the 90-degree phase of the input signal, and it's going to sample that quarter cycle. Likewise, the third output will start sampling at 180 degrees, and it will see the third quarter cycle, and the last output will start sampling at 270 degrees and see that last quarter cycle of the RF input signal. Now you'll notice that there are capacitors on each of these outputs, and the reason that they're there is simply to sample and hold the voltage that they see. So they're just going to track whatever voltage they see while the RF input is connected to them. So for example, this first output, the 0-degree output, is going to track this red portion of the signal. And so when we switch over to the second output, that first output, the 0-degree output, will be stuck at this peak voltage value. Likewise, the second output that starts sampling at 90 degrees is going to see this quarter cycle voltage, and it's going to stop sampling here because we're going to switch over to this third output. And so it's going to be stuck at 0 volts because this is the 0 volt potential of the signal. The third output will sample, of course, the third quarter cycle, and so it's going to track this voltage down to the minimum voltage of the input signal, and so you'll see a minimum voltage here, and this last quarter cycle will again end up being 0 volts because it's going to track this last portion of the signal, and that's going to end at 0 volts. So what you'll see if these two inputs are at the same frequency is that this will be a peak value, this will be a minimum value, and these two will simply be 0 volts, and they will stay that way. There'll always be this constant voltages on all four outputs. However, what happens if the RF signal is a slightly different frequency than the local oscillator? Well, as we saw in the oscilloscope, when they're of different frequencies, we're going to start seeing this kind of phase shift over time. And so these outputs will start seeing different voltages applied to them, and so the capacitors are going to track those different voltages, and those voltages are going to shift over time at the rate of the frequency difference between the RF and LO inputs. So what we get out is basically our downconverted baseband signal. If these two are 1 kilohertz away from each other, then we'll end up getting this 1 kilohertz output from this 4-to-1 multiplexer. And we get that in 4 parts. One part is the 0-degree portion, one part is the 90-degree portion, one part's the 180-degree portion, and the last part is the 270-degree portion. So we have our quadrature outputs here. And in fact, each of our quadrature outputs has complementary outputs. So 180 degrees is complementary to 0 degrees, and 270 degrees is complementary to 90 degrees. So what you'll often see is that these complementary outputs will be put into a differential amplifier so that we're not just throwing away this portion of the signal. And a practical implementation of the Tayloe mixer is actually quite simple. You can use any 4-to-1 multiplexer chip pretty much although the classic is to use the 3253, which is actually a dual 4-to-1 multiplexer, and that's what I'll be using in my receiver design. So you can see that the local oscillator inputs, the two quadrature inputs from the local oscillator, are applied to the S0 and S1 inputs on the multiplexer chip. And the RF input is biased to half rail. And that's just so that we can get the maximum voltage swing on the RF input here, because this is a single supply design. Now, the RF input, you'll notice, is actually applied to the inputs of both of the 4-to-1 multiplexers on this chip. And that's really just done to lower the resistance that this chip provides to the signal. So the typical input resistance of each of these is 4 ohms. So if you use both of them in parallel, that drops the total resistance to 2 ohms. And likewise, we can see that the corresponding outputs have been tied together as well from those two internal multiplexers. Now, the way that you select these sample capacitors is basically to set the low-pass cutoff frequency that you want. Because whenever the RF input is applied to one of these outputs, the resistance of the RF input, which is typically 50 ohms, provides a low-pass filter in conjunction with this capacitor. Now, it is important to note when you're calculating the cutoff frequency for this low-pass filter that because each output only sees the input 1/4 of the time, it effectively only sees 1/4 of the input resistance. So if you have a 50 ohm input resistance here, the total resistance that this sees would be 50 ohms plus the 2 ohms of resistance here divided by 4, which is 13 ohms. So with a 0.1 UF capacitor here, that gives a cutoff of about 120 kilohertz. And that's probably a bit high for what I'll ultimately want to use for this application, but for right now, they'll work just for testing. Likewise, you'll notice I'm only looking at the I and Q outputs here, the 0 and 90 degree outputs. I'm not looking at the 270 degree output or the 180 degree output, although I will probably be using those later on in the design. So I've added that mixer circuit here on my receiver board, and as we've seen from previous videos, I have a 28 megahertz oscillator that's being fed into a dual D-type flip-flop, and that divides the frequency by 4 down to 7 megahertz and provides the I and Q quadrature local oscillator outputs that I'm feeding into the mixer. And I'm also providing a 7 megahertz signal here to the RF input on the mixer, and we can see I've got that inductor here for setting up the bias on the input for the RF, and a little resistor divider here if you can see it. And I've added some decoupling capacitors here that I didn't show on the schematic, but yeah, whenever you're dealing with RF, you definitely want to have some good decoupling there on your power supply lines. So we'll take a look at the I and Q outputs from the mixer and see if we get what we're expecting. And my RF signal is currently 1 kilohertz above my local oscillator frequency. And we can see that my I component is leading the Q component just as we'd expect. And if I change that to be 1 kilohertz below the local oscillator, there we go. Again, 1 kilohertz difference, but my Q is now leading the I component because it's below my local oscillator, just as we'd expect. So that seems to be working just fine. So this 40-meter receiver project is shaping up quite nicely. Obviously, there's still some more work to do. I'll have to put in some work on the RF front end here and, of course, add some additional amplification and probably some filtering on the output of the mixer here. But hopefully this video has cleared up some concepts about quadrature signals and quadrature mixing, and specifically using the Tayloe mixer in a direct conversion receiver design. So I hope you enjoyed the video, and as always, if you have any questions, suggestions, or corrections, leave them in the comments down below, and thanks for watching.